And good morning to everyone. I hope your day is going well so far, and if it's not going well so far, I hope it gets better. Today we're going to be doing our activity for section 7.2 and 7.3 about sample means and sample proportions, all under the umbrella of chapter 7, which is sampling distributions. Hopefully this activity will help make this make more sense or help this make more sense. And if it doesn't, then we'll figure out something that does. So, there's that. So with that, the thing I need to do is give you guys the link to the activity. So we're going to drop that in the chat. There we go. Should be in the chat now. So please log into the activity. As usual, I have you guys locked on that first page of the Desmos activity. So when you log in, please just respond to that question. And if you don't have anything that you'd like me to know today, that's fine too. The question is just, what would you like me to know today? If you just need to vent, please vent. If there's something you'd like me to be aware of, please let me know. It's up to you. Take a moment, answer that question. That is kind of like our check-in for today. It is anonymous. No one else can see your responses, just me. All right, so let's take a moment, get logged in, and get ready to do some work. Here's our check-in screen. All right, thank you for those of you who have responded. I am not going to take time right now to read all the responses. I will read them after class. I read really slow, guys. But I will get to those. I hope your day is going well, or at least it's starting to go well. But yeah, thank you for checking in. We're going to open up to the second screen now. So you have access to both. And this first screen, if you're looking at it on your own activity screen, or if you're looking at the shared screen, right? The sampling, distributions, proportions versus means. This is just a copy of one of the last slides from our presentation yesterday. And it's just a side-by-side look at sample proportions and sample means, right? The notation that we use for those and the formulas and conditions that we need to check, right? So with sample proportions, the mean of the sample proportions is equal to the proportion of interest from the population, right? And that's what the variable P represents, proportion from the population. It's our parameter. Standard deviation of the sample proportions is equal to the square root of the proportion of interest from the population times 1 minus that proportion divided by the size of our sample, which is n. Right? The standard deviation is only valid, so to say, if the 10% condition is met, which means that our sample size is less than or equal to 10% of the entire population we are sampling. Right? And as n increases, the sampling distribution becomes approximately normal. We check the large counts condition to make sure that this holds. Right? The large counts condition says that essentially if the number of successes and the number of failures are both greater than or equal to 10, or at least 10, then large counts condition has been satisfied and our sampling distribution is approximately normal. And we do that by doing n times p, right? And n times 1 minus p. Right? So there is that. Yeah. So that's sample proportion, sample means, looks very similar. Right? The mean of a set of sample means is the mean of the population. Standard deviation of our sample means is equal to the standard deviation of the population divided by the square root of the sample size. Once again, for standard deviation to be valid, the 10% condition must be satisfied. If the population distribution is normal, so if our population was normal, the sampling distribution of X bar, or the sample means, will also be normal. And the central limit theorem says that when n is large, greater than or equal to 30, which means our sample size is greater than or equal to 30 individuals, the sampling distribution of the sample mean X bar is approximately normal. So for each of these, we have a condition to be able to find or calculate the standard deviation. That's the 10% condition. And there's an extra condition to say that the distribution of the sample means or sample proportions is approximately normal. Right? It's a large counts condition for sample proportions. It's central limit theorem for sample means. So these are the things that we need to keep in mind as we work through the activities today and the problems. Is there anything I can clarify so far? So then we're gonna work into the first two problems here. Before I open them up, we're just gonna talk about them real quick. So you please switch back to, well, actually, you know what? No big deal. Let's open them up. You guys can start on those. So the first matching problem, right? The SAT math scores, there is a context, right? That's the box with a lot of the words in it. And then there are these extra notations and numbers, right? 4 of these match up with the context. You need the proper parameters, right? Mean and standard deviation, and statistics, sample mean, right? The mean of the sample means and the mean of the sample, the standard deviation of the sample means, right? So there's 4 things for this context. There's 2 extra cards, right? So once you've matched these up, you should have 2 left over that don't match to anything. In the next one, the PEDs in college sports, you're doing the same thing, right? This is a sample proportions example. So there's a context, there is a population proportion, then there is a mean of the sample proportions and a standard deviation of the sample proportions. So there are 3 cards that match to this context in the second matching problem, and 4 cards that match to nothing. So they don't need to be grouped, they just stay somewhere else on the screen. Right? The extra cards in both scenarios are just common mispairings of the values and variables. Okay, so they're kind of there to throw you off, and it's check and see if you're understanding how the context and the notation and the numbers all go together. All right, so you should please start working on the first 2 matching problems. Alrighty, now I know that that probably wasn't enough time to complete all of this matching. So thank you for attempting. We're going to check on the results for this, right? And see how this was supposed to be paired up. So if you would be so kind as to go back to the SAT math scores portion, or if you want to follow along on my shared screen, you're welcome to do so. I'm going to arrange these. So our context here is the scores on the math portion of the SAT exam in a recent year were roughly normal, with mean 515 and standard deviation 114. You choose an SRS of 100 students and average their SAT math scores. We do this many, many times. That creates our sampling distribution. So the population mean and standard deviation are provided at 515 and 114. Right? The notation that goes with those is mu for the population mean, 515, and sigma equaling 114 for the standard deviation. Right? Regular mu, no extra symbols on it. Regular sigma, no extra symbols on it. Those apply to the population. So that leaves us with these other 4 cards. Right? We have mu of x bar twice and sigma of x bar twice. We just need to identify which one is the correct pairing with the number. We'll look at the mean of the sample means. That should be 515. Right, and that's because if we look back at our notes here, the mean of the sample means is the mean of the population. They're the same value. Okay, so the mean of the sample means is 515 because the mean of the population is 515. Then the correct standard deviation for our sampling distribution of sample means, right, sigma of sample means is 114 divided by square root of 100. And again, this goes back to our formula, right? The standard deviation is sigma divided by square root of n. N is the sample size. Our sample size was 100. These other two don't go anywhere. Okay. So anything I can clarify on this example? Right. So there are 4 cards that match to that context. The next context, there's a lot more extra cards. There's a lot more things to be confused by. Right. For this one, we have PEDs in college sports. The magazine Sports Illustrated asked a random sample of 750 Division I college athletes. So that's the size of N. Do you believe performance-enhancing drugs are a problem in college sports? Suppose that 30% of all Division I athletes think that these drugs are a problem. So the 30% is the population proportion. That's the value of P, which would be 0.30 as a decimal. Right, we're going to let P hat be the sample proportion who say that these drugs are a problem. So the first thing we can do, given these things, because we have P, mu of P hat, mu of P hat, right? We have all these kinds of craziness going on. We have the population, oops, sorry, wrong P. Population proportion is 0.30. Because 30% of all Division I athletes think this is a problem. So then we are looking for the mean and standard deviation of the sampling distribution of sample proportions, right? So that leaves us with, we can choose from this one, and this one, P equaling 750. That's not true. 750 is the size of the sample. That would be N. P hat would be the proportion in a single sample. We don't know what that is. We're not given that information. This, one of the P hats is 0.3 times 750. That's just, if the proportion held true for that sample, then we'd have 225 out of 750 who think it's a problem. The other P hat is equal to the sample, or equal to the population proportion. We know that that is not true. So we're left with these 3. There's only one for a mean, so we're going to pick that one. The mean of the sampling distribution of sample proportions is equal to the population proportion of 0.30. And that goes back to our formula, our definition here for the mean when the sampling proportions, the sample proportion. Then the correct sigma is sigma of P hat, or the standard deviation of the sampling distribution of sample proportions. It's the square root of 0.30 times 0.17 divided by 750. And again, that is the formula we would expect from our definitions. Is there anything I can clarify? I know this was a little confusing. All right, so then, hopefully that helps a little bit. We're now I'm gonna open up the next 4 problems, right, in just a moment. All right, for these, let's see, I want to try that again. Yeah, we'll do this. So for these next 4 problems, right, it'll be screens 5, 6, 7, and 8. We're gonna put y'all into some breakout rooms so that you can hopefully work together. That's the idea, is that you guys talk to each other and help each other out and come to a consensus on how to do these things. So if you give me a moment, I'm going to put y'all in rooms. This is kind of just random. So I apologize if you don't like who you get paired up with. Okay. So everyone's been assigned to a room. Right? Hopefully everyone is actually in the activity that's in the room. So we can open up the rest of these guys up to there. All right. So these next 4 problems are contextual problems, right? Do you understand the concept, right? 10% condition, large counts condition, right? The Scrabble problem is asking if these conditions have been met for a proportion, and the central limit theorem. You may want to refer back to your notes to get answers to these problems. Very good. All right. Awesome. Welcome back. Okay. So let's talk about these problems now. Right? The 10% condition, many of you, so if we go back to this 10% condition screen here, I will actually share my screen again. That makes it a little easier. If you'd like to follow along on the shared screen, you can. So 10% condition, what is 10% condition, and for what value do you need to make sure it is met before finding it? Right? Many of you who responded to this question had it correct. The 10% condition says that we need to have a sample size that is less than or equal to 10% of the population. I saw many responses that were right along those lines, so that is excellent. You also needed to mention, to fully answer the question, that the 10% condition must be met in order to find the standard deviation. Otherwise, we can calculate standard deviation, but it's not valid. Right? Our sample size may be too large. Right? We have to do a different type of calculation. Okay, so our 10% condition needs to be checked before finding a standard deviation, or at least to validate the standard deviation. All right, our large counts condition, right, for sample proportions. Right, what needs to occur for the large counts condition to be met? Right, and if this condition is met, what can you assume about the sampling distribution of the same proportion p hat? Right, the large count conditions, I saw some people typing into their responses here. You know, if NP and n times 1 minus p are both greater than or equal to 10, that meets the large counts condition, meaning there's at least 10 successes and at least 10 failures, right, in our sample. As long as that's met, we can then assume that our sampling distribution for the sample proportions are approximately normal, and we can then use normal calculations, table A, standardizing score, all that fun stuff to find probabilities with our sampling distribution. So that's 10% and large counts condition. We have our example for a proportion, right? We have the game of Scrabble. Each player begins by drawing 7 tiles from a bag containing 100 tiles. There are 42 vowels, 56 consonants, and 2 blank tiles in the bag. So we're not directly given proportions. However, we can use the given information to find a proportion, right? There's a 42% chance of getting a vowel because 42 out of 100, or 0.42 probability, or proportion, sorry, not probability, proportion. We have a 0.56 proportion of consonants, a 0.02 proportion of blank tiles. So we have proportions for the population. They're just not directly given as like decimals. Right. Mr. Mosley chooses an SRS of 7 tiles. Let p hat be the proportion of vowels in my sample. Right. Is the 10% condition met in this case? Right. In other words, is 7 less than or equal to 10% of 100? Yes, 7 is less than or equal to 10, so this condition is met. And for the reason I just explained. The large counts condition, is this condition met? Well, n is 7. 7 times 0.42 is less than 7. I think it's going to be right around like, I don't know, 3. Right? Less than 10. Right? So large counts condition is not satisfied. Right? And that is because my sample size is only 7, so it's impossible for me to have more than or at least 10 successes and at least 10 failures when I only have 7 to choose from. So large counts condition is not satisfied. It means I cannot say that the sampling distribution is normal. All right. Any questions about this example? So again, yes to 10%, no to large counts. Pardon me. The central limit theorem. For our purposes in this course, what sample size n is considered to be large enough for the central limit theorem to be used? The answer to that question is the sample size must be greater than or equal to 30. That is our mark for large enough, at least 30. N has to be greater than or equal to 30. What does it mean about the sampling distribution of x bar if the sample size n is large enough? It means that the sampling distribution of x bar is approximately normal, and we can then use normal calculations to find probabilities of certain outcomes. So this is essentially the large counts condition for a sample sampling distribution of sample means. Right? It's the central limit theorem. Okay. Is there anything I can clarify about what we've covered so far? Okay. So then we're going to jump to the next problem. Right. So this is students on diets. This one we're actually going to have to do some work, do some calculations, and we're going to use table A, as long as the proper conditions are met. And I'm going to push everyone over to screen 9 here. Give me just a moment. There we go. Come on, guys. All right. So in this example, we have a sample survey of interviews. A sample survey interviews an SRS of 267 college women. Suppose that 70% of college women have been on a diet within the past 12 months. What is the probability that 75% or more of the women in the sample have been on a diet? All right. To do this, you will need to calculate the mean and standard deviation of the sampling distribution of p hat. Check the 10% and large counts condition. Then if the conditions are met, you can use normal calculations to find the probability. All right. Please only input the probability in the form of a decimal and round to 4 decimal places. There is no need to input how you calculated it or the probability notation. Right? Just the number is fine. Okay. So you probably want to start by identifying sample size. Right? What is the population proportion that I'm interested in? Okay, find the mean and standard deviation of the sampling distribution. check our conditions, and then we can use normal calculations, right? I'm going to give you guys 5 minutes essentially to start on this process. You will not probably be able to finish it, and then we will talk about it. All right, so we're going to put 5 minutes on the clock. Please work on this problem. This is a possible way of what the work could look like up to a certain point here. This is what I was doing after I did a couple other things. So our N in this population or in this survey was 267. P, the population proportion, is 0.70. The P hat is defined as a proportion of women who have been on a diet from the sample survey. The mean of P hat is 0.70. Standard deviation, because 267 is less than 10% of all college women, and the 10% condition is met, is 0.028. We use the formula for sample proportions. And then we want to find the probability that P hat is greater than or equal to 0.75, which is equal to 1 minus the probability that P hat is less than or equal to 0.75. We're going to standardize 0.75 by finding the z-score. Z equals 0.75 minus 0.70 divided by 0.028, barring myself making any errors, which hopefully I have not. And we get, that makes sense, 1.7, about 1.79 if we're rounding to the 2 decimal places. Right, we then find 1.79 on table A, right, which is not where I left it. Go to our positive side of table A, and we want 1.79, so we're going to find 1.7. Follow that to the end, 0.09. We get 0.9633. Right, so that means that the probability of Z, right, being less than or equal to 1.79 is equal to 0.9633. And that is found on table A. So we get 1 minus 0.9633. We get 0.0367. Is the probability that P hat is greater than or equal to 0.75. And again, I'm using the complement rule because the table A only gives me less than or equal to. It does not give me greater than or equal to. So we use the complement rule. Right, so the probability, right, we go back to answering our question. Probability that 75% or more of the women in the sample have been on a diet. I have a probability of about 3.67%, 0.0367. Okay. And if you were off by some decimal places, or if I was off by some decimal places, hopefully I wasn't, you know, that's okay if it's a little bit off based on rounding errors. Right, is there anything else I can clarify? All right, so we're not going to get to the last example here today. You are more than welcome to check it out on your own, the bad carpets example, if you like. That's up to you. As a final thing, if you want to do the lesson wrap up, right? Please do so. Let me know how the lesson went, what you thought. I'm open to anything. If you think it was bad, tell me it was bad. That's fine. I can take it. Let's see. The practice problem solutions are all posted in Canvas now. You now have those available. So if you've been doing the practice problem sets, solutions are now available. You can check your work. Yeah, other than that, there is no school on Friday. So we only have one more day of school to get through this week. And then there's no school the following Monday either. We had a nice 4-day weekend. So please keep that in mind. If there's anything else I can help you guys with, if you have any other questions, please let me know. Other than that, I will see you next week. Have a lovely weekend. I hope you have a great rest of your day.